So where are we in the general case? So we know that in this case there are exactly Q values and they're all equally spaced along a circle of radius r centered at the origin, where r is the absolute value of z raised to 1 over q. Now the question is, why does z to the p over q have exactly q values, just like z to 1 over q? And remember, we have made this assumption that p and q are relatively prime. In other words, p over q, the rational number p over q, is in its reduced form. To prove that there are exactly q values for z to the power p over q, we know that to get z to the power p over q, we have to raise every one of the cubed roots of z to the power p. When we raise these to the power p, the absolute value becomes r to the p, and each of these arguments is multiplied by p. So now, is it possible that two different one of these, when multiplied by p, will give you the same argument? So let's see. What does it mean? First, each one of these arguments can be written as theta plus some integer times 2 pi over q. So that integer has to be either 0, 1, 2, or all the way to q minus 1. Because when you get to q, going around the circle, we go back to the original one. So here j is 0, here j is 1, j is 2, 3, and so on. So let's, just like j, we can choose k to be some other factor here. Now if we multiply these arguments by p, then they have to equal up to some multiple of 2 pi in order to be the same. So let's see what happens if they are the same. We're making this assumption here, and we're setting these to equal. Now your task is to prove why j and k cannot be two different indices. And the assumption that is very important is that p and q are relatively prime.